Hi, everyone. So we've gotten to the point in the semester where we need to look at the nature of light. What is light? What is it made of? Um, so that we can understand the information that we receive from light. Everything beyond the solar system that we study, we know about from the light we receive. We can't travel there yet. So in order to understand about these objects, stars, nebula, galaxies, we need to see what the light is telling us, decode what the light is telling us so that we can study the nature of those objects. Um, Light is a wave made of electric and magnetic fields. So you could call it an electromagnetic wave, right? Objects with an electric charge create electric and magnetic fields around them. And when those electric and magnetic fields oscillate up and down and create waves, those waves propagate forward at the speed of light. That's the special thing about light, is that light always travels at the same speed. But light can have different wavelengths and different frequencies, right? The shorter wavelength light is going to oscillate at a higher frequency. Longer wavelength light is going to oscillate at a lower frequency, so that if you have longer waves, you get fewer of them per second. If you have shorter waves, you get more of them per second. Wavelength and frequency are inversely proportional, but when you multiply wavelength times frequency, you always get the same speed. When we study wavelengths of light, wavelengths essentially are synonymous with color. What our eyes perceive as color is just light of different wavelengths, specifically of the visible spectrum. Our eyes are sensitive to light of wavelengths between 700 nanometers at the red end. Red light is the longest wavelength light that our eyes are sensitive to, down to violet light, which is the shortest wavelength light that our eyes are sensitive to, at 400 nanometers. These are not all the wavelengths of light. If you want to look at all of the wavelengths of light, now you're looking at the full electromagnetic spectrum, where on the long wavelength end, the frequencies of light that are, sorry, I should say, the wavelengths of light that are longer wavelength than visible are the infrared and then the radio waves. Radio waves are the longest wavelength and therefore the lowest frequency light of the spectrum. On the short wavelength end, the light that is shorter wavelength than violet light is the ultraviolet, and then the X-rays, and then the gamma rays. So gamma rays are the shortest wavelength, highest frequency light in the universe. But regardless of the wavelength and the frequency, all light travels at 3 times 10 to the 8 kilometers per second. Or in a lot of the homeworks, they refer to it as 3 times 10 to the 5 kilometers per second. All light, regardless of wavelength, regardless of frequency, it all travels at 3 times 10 to the 8 meters per second. The other important thing to know about light is that light waves are broken up into these packets of light waves, these chunks of light waves that are called photons. You can kind of think about a photon as being a particle of light. It's kind of got a beginning, and then you have the light waves, and then it kind of comes to an end, and this packet travels at c, at the speed of light. Right? In most physics equations, c, the same c that we're using here, is the speed of light. A photon, a particle of light, if you will, contains a certain amount of energy. Right? It takes energy to make light, and when that light travels outward at the speed of light, that photon carries its energy with it in the form of those oscillating electromagnetic waves. It turns out that the energy of a photon is equal to h, which is what's called Planck's constant. It's another constant of nature, much like the speed of light, times the frequency. The only variable here is the frequency. right? H is a constant. So that the higher energy light, higher energy photons are higher energy because they have higher frequency and or shorter wavelength. Right? Frequency and wavelength are inversely proportional. So if we take this formula here, that's c, the speed of light, equals wavelength times frequency, then we can substitute the expression in here for frequency, and we have the speed of light divided by wavelength. So that why are high energy photons high energy? Because they have short wavelength. Low energy photons are low energy because they have long wavelengths. So that's light in a nutshell. Light is defined by its wavelength, its frequency, its speed, and its energy. When you want to study the light from a star, if you want to study that light in more detail, you can do that by taking the spectrum of an object. So the spectrum is where you take all of the light coming at you from a star, a planet, a nebula, a galaxy, anything. Take all the light coming from that object and shine it through a prism to break that light up into the different wavelengths. Break all of that light up into the different colors so that you can study how much light you're getting at each wavelength individually. Basically, you're taking all that light and slicing and dicing it up into the different wavelengths to get some more detailed information about the object giving off that light. There are, in nature, 3 basic types of spectra that you see. We're going to talk about the first one in this lecture, the continuous spectrum. A continuous spectrum is what you get emitted by a hot, dense object. So when you have a hot, dense object, that object is tightly packed in, right? It's dense. The atoms are tightly packed in, and because the object is hot, all of those atoms in that dense object are moving around fast and they're colliding with each other. And so when those atoms collide, in a collision, some atoms gain energy, some atoms lose energy, and some atoms are going to be so energetic, they're going to gain so much energy that they can give off light, that they can lose their energy in the form of light, and then the object begins to glow. And when you have these dense objects giving off light, the shape of its spectrum looks like this. This is a graph of intensity versus wavelength, or you could say brightness. Brightness of light at those different wavelengths versus wavelength. And with these dense, hot objects, you always see a little bit of short wavelength light, a little bit of long wavelength light, and it's brightest somewhere in the middle. This is, you could call this a continuous spectrum. It's called a continuous spectrum because that light emits this smooth function, which the homework calls the Planck function. This is also, by the way, called a Blackbody spectrum for historical reasons, or the thermal spectrum, because the spectrum depends on the heat of the object, the temperature of the object. So if you take a dense hot object, like let's say the surface of a star, right? The surface of a star is hot, it's dense, it's giving off light. If that star has a temperature of 3000 Kelvin, it's going to give off a little bit of short wavelength light, a little bit of long wavelength light, and it's going to peak right about here at this wavelength. When I say peak, I mean the wavelength at which that spectrum is brightest is about 1000 nanometers. If we heat the surface of this star up to 5800 Kelvin like the sun, notice that the graph moves upward, so the star gets brighter at all wavelengths, but also the peak has shifted to now that star is brightest at about 500 nanometers. The peak, the brightest wavelength, has shifted to shorter wavelengths. If we heat this star up all the way to 15,000 Kelvin, it gets very bright at all wavelengths, and now this star is brightest all the way over here in the ultraviolet. So that when you take a dense object, as you heat it up, what happens? The object gets brighter, and also it's preferentially giving off short wavelength light. the peak, the brightest wavelengths, shift to shorter and shorter wavelengths. And what color are shorter wavelengths? Bluer. Shorter wavelengths are bluer light. So that as you heat this dense object up, the object gets brighter and it also gets bluer. Right? This object here, the 15,000 Kelvin star, is giving off a lot more blue light than red light. So to the naked eye, the star looks blue. This cool star, this 3,000 Kelvin star, is giving off a lot more red light than blue light. To your eye, that star would look red. So that your eye can do a rough measurement of the temperature of a star. Red stars are red because they're cool. Blue stars are blue because they're hot. And our sun, sort of being in the middle, is about uniformly bright all the way across the spectrum. It's not preferentially giving off blue like this or preferentially giving off red like this. There's a simple relationship between the temperature of that object and the brightest wavelength, the peak wavelength we're calling it here. This lowercase lambda here, by the way, is the symbol for wavelength in these equations. So the lambda with the subscript peak is one way of saying, what am I talking about here? I'm saying that the peak wavelength, the wavelength of this peak, the wavelength at which the star is brightest, here, or here, or here, which is to say this wavelength, or this wavelength, or this wavelength, is only determined by the temperature of the object. The hotter it is, the bluer it is. If the temperature goes up, the wavelength of the peak goes down. The peak wavelength gets shorter and therefore bluer. This gives us a huge piece of information. The surface of a star is dense, it's hot, it's going to emit light like a black body. We don't know what the temperature of a star is. You can't just point your telescope at a star and automatically know what its temperature is. But this is something we can measure. The peak wavelength is something that's measurable. So this relationship here is what's called Wien's displacement law. But we can rearrange this to say, well, let's rearrange the algebra to solve for temperature. Now, all we need to do is look at a star, take the light from that star into our telescope, split the light up into the rainbow, like we've done here, split the light up into the rainbow and say, what is the brightest wavelength? And once you've measured the brightest wavelength, once you've measured the peak wavelength, you can plug it into that equation and you can have the temperature. This number up here on the top is a constant. It's just the constant that shows the relationship between temperature in Kelvin and the peak wavelength in nanometers. So 2.9 times 10 to the 6 nanometers times Kelvin. So you plug the peak wavelength in nanometers here. The nanometers on top cancels with nanometers on the bottom. And the unit that survives is the temperature in Kelvin. This becomes another observable, another measurement that we can make in our spreadsheet. We can measure the peak wavelength. I'll just shorten that to that. All right. That is, the peak wavelength is something that you can measure directly in your spectroscope from the spectrum of a star. So if you measure the peak wavelength of, let's say, 500 nanometers like the sun, right, we can use Wien's law to determine the temperature of the star. The temperature is 2.9 times 10 to the 6th divided by the peak wavelength in nanometers. So the temperature is going to equal 2.9 E6 divided by the wavelength in nanometers, and that should give us the temperature of the surface of that star in Kelvin. And lo and behold, you get the temperature of the sun, 5800 Kelvin. Now we know a third property of this star. Based on the three measurements that we can make, parallax, flux, and peak wavelength, we can get the distance, the luminosity, and the temperature. We can do better than that, though, because notice that these graphs here, these graphs of the spectrum, are graphs of intensity per square meter per second, right? These are graphs of energy or in other words, luminosity. These are graphs of luminosity at different wavelengths versus wavelength. So if you add up all of the light that this star emits, added up all across the spectrum, we could get the total luminosity of the star. So let's just do that. If we add up, let's take this red star here, right? If we add up the light that it gives off at this wavelength, plus the energy of light it gives off at this wavelength, and that wavelength, and this wavelength. Basically, if we add up the full area under this curve, if we take the full area under this red curve, we will have added up the energy given off per second, added up across the whole spectrum for the star. We've got the luminosity. And so you can look at these stars and say, well, this red star, it's got a small area under the surface. That's going to be a dimmer star. The blue star has a larger area under the surface. Sorry, a larger area under the curve, I should say. It's going to be a brighter star. Notice, nowhere in this discussion have I said that it depends on what the star is made of. A continuous spectrum, a blackbody spectrum, is given off by an object because it is dense and based on how hot it is. Right? The shape of the Planck function, the shape of the spectrum, the peak in the spectrum, the entire shape of the spectrum, only depends on temperature. That's why we're able to use this to figure out the temperature, because the temperature, the peak wavelength is only determined by the temperature. So measure the peak wavelength and you can tell what the temperature of the object is. It doesn't tell us anything about what the star is made of. All we know is it's dense and it has this temperature. And if we can add up the full area under this curve, we can get the luminosity. So let's look at object D here. Object D, again, this is a graph of energy output per second, which is another word for luminosity, versus wavelength. If you add up all of the area underneath this curve, you add up all of the light given off by this star, added up across the whole spectrum, this is a pretty big area. This is a pretty bright star. And yet this star peaks in the red light. The peak wavelength is in the red, and a red star is cool. How can this be? How can you have a star that is very bright, it's giving off lots of energy, even though it's not very hot? It's cool, it's red. And the answer is because the luminosity of a star depends on its temperature, yes, but it also depends on the size of the star. Because the light from a star escapes through the surface. And so the more surface area that star has, the more area there is available to let the light out. And if the star can let more light out, the star is going to give off more light per second. It's going to have a higher luminosity. So 4 pi radius squared, that's the formula for the surface area of a sphere, like a star. Sigma times temperature to the fourth, that's the luminosity per unit area. This is the sigma t to the fourth is what's called Stefan Boltzmann's law. That's the energy given off from each square meter on the surface. So we have an expression for the energy given off per square meter times the number of square meters gives us the full luminosity of the star. The little sigma here is what's called the Stefan Boltzmann constant, is this value right here. This equation, by the way, is in SI units, right? Luminosity is in watts, radius is in meters, temperature is in Kelvin. So that's why the Stefan Boltzmann constant, or this is why the Stefan Boltzmann constant has this crazy unit system, is because you want your meters here, you want your meters squared here, and your Kelvin to the fourth here to cancel out and leave you with just luminosity in watts. But hey, this is true. This relationship is true for any star. Well, we can determine the luminosity of a star, right? We've got the flux and the parallax. If you've got the flux and the parallax of a star, you can figure out luminosity. If you've got the peak wavelength of a star, you can figure out temperature. If we know L and we know T, we can solve for R. So let's rearrange the algebra here to solve for the radius. Now, I'm going to do you a little favor here. I'm going to convert this equation into solar units. So instead of measuring the radius in meters, which would be ridiculous because the radius of a star in meters is a huge number. Let's just convert this into, this is the relationship for the radius of a star in solar radii. In other words, how many times bigger than the sun is that star? How many times the radius of the sun is that star? And the radius of that star in solar radii is equal to the square root of the luminosity in solar luminosities divided by temperature in Kelvin over 5800 Kelvin, which is the temperature of the sun, squared. You can't just look at a star and know what its radius is. Every star outside of our solar system is too far away. The stars look like little pinpoints of light. You can't just look in your telescope and see which ones are the big ones and which ones are the small ones. They all look infinitesimally small. But if you know the luminosity and the temperature, we can figure out which ones are the big ones and which ones are the small ones. So let's see how we can do that. If we know these three observables, we can solve for luminosity, we know temperature, and now we can know radius. The radius of that star in solar radii, which I'm going to symbolize our sun. The radius is the square root of luminosity. Right? SQRT is usually the shorthand for square root in most spreadsheet programs. So I got the square root of luminosity in solar luminosities, which is the way I want it, divided by the temperature over 5800 squared. I've got the square root of luminosity divided by temperature over 5800 squared. This should give me the radius of this star in solar radii. So based on these numbers that I just made up, this star is the same temperature as the sun, and yet it's a much lower luminosity than the sun. How can that be? Why is this star so much fainter than the sun? Why is it a tiny fraction of a solar luminosity when it's the same temperature? And the answer is because it's a lot smaller than the sun. If I changed my numbers so that I was getting a much brighter star, well, then this star would have a luminosity of it's brighter than the sun. Why is it brighter than the sun when it's the same temperature as the sun? Well, it's because that star is bigger than the sun. So now we know three properties of this star. We know how bright it is, we know how hot it is, and we know how big it is based on the three things that we can measure in our telescope. Have a good day, everybody.